let's learn about inductance. Inductance is the property of an inductor, which is simply a coil of wire. So the standard simple inductor is just a coil of wire. Here we look at the coil from the edge, and here we can look at the coil down the end. So we build a simple circuit with a battery, a two-way, three-way switch, open, closed here, and a resistor, and an inductor. The symbol for inductance is L, and what happens when I close the switch? So pause the video and answer that question. So let's lower the switch. It doesn't look like it's going to reach, but I'm just going to draw a line in there. So we've closed the circuit here, and what you should have said is current flows through the circuit this way. But if you've studied inductors, you know that you can't instantaneously change the current through an inductor. So when we first close the switch and the current tries to go through the inductor, it will induce an EMF in the opposite direction, which stops the current. Well, it doesn't really stop the current, it slows the current down. So what we want to do now is understand why when I try to put current through here, the coil responds by slowing down the rise of current, making it difficult for current to rise. So the inductance is kind of like a resistance, right? Our resistor opposes the flow of current, and we even define resistance as the ratio of voltage to current. So this is as if a high resistance means for a given voltage we'll get a small current. And what happens in the inductor that it opposes the rise of current? See if we can answer that question. Okay, I forgot to pause. Here's the explanation. When current, we start with a coil and there's no flux through the coil. So what we're going to use, let me write it down. We need to refer to Faraday's law. I'll write it down here. We get an induced EMF, which is influenced by the number of windings in the coil. So a coil with more windings is going to have more inductive EMF, and how much you get depends on how fast the flux changes. Hard to fit that there. So as when I close the switch, the current starts to flow, and as the current starts to flow, using right-hand rule number 3 for a coil, current circulating this way, clockwise, gives rise to a flux. It gives rise to a field through the coil that goes into the page. So what we're picturing is, remember, we have to picture not so much the flux, but the change in flux. So the picture looks like this. I close the switch, and I see an increasing amount of field through the coil. Let's trace the sequence of events here. So we have, I close the switch, the current, I'm going to erase that. When When I close the switch, the current in the circuit rises. This in turn gives rise to a field. Can I squeeze this in? Mu naught N over L times I, which is increasing, right? As the current rises, the field will rise. And as the field rises, the flux, magnetic flux, BA cosine theta, didn't get that in there, the flux rises. So increasing current leads to increasing field, leads to increasing flux. So we see an increasing flux through this coil. What happens? Answer that question. Well, I hope you answered it. So here's the answer. We look at Faraday's law. We see that there's a increasing flux through this coil. We need Lenz's law as well. So that means there's an induced EMF. Then we go to Lenz's law, which says that the induced EMF will tend to produce a current, which produces a flux, which opposes the change. Should I write that down? Remember Lenz's law? Oppose the change in flux that's producing the EMF. So that means that through this coil, the induced EMF will try to drive a current. The current's going this way, it will try to drive a current in the opposite direction because the current this way is producing a flux into the board, so it'll tend to slow the current down. It'll induce an EMF which opposes the battery EMF, sometimes called the back EMF. So the natural Faraday's law, inductive response of the coil is to slow down the rise of current. So let's see what that means. So keep in mind this statement. Current through a coil cannot change instantaneously. Why not? There's the answer. Make sure, be clear that you understand it. The rising current will cause a rising or falling field. The rising or falling current, rising or falling field, rising or falling flux induces an EMF which is going to oppose whatever the change is that's causing the rise and the fall of current. So we're back to our circuit with numbers in it. We have the battery voltage. I've given a value of 6 volts. We have our three-way switch. We have our resistor, which has 3 ohms of resistance, and our inductor, which has 2 henries of inductance. And we want to ask the question, what happens? We want to trace the time-dependent behavior of the current in the circuit, and the voltage across the inductor, and the voltage across the resistor. So we want to understand the behavior of this circuit. It's time-dependent behavior. So let's see if we can puzzle out all of these parts. We'll look at the voltage across the resistor. Well, let's look first at the current through the resistor. The voltage across the inductor. And so on the y-axis I'm plotting these values, and on the x-axis we have time. So see what you know. See if you can do those graphs. Okay, here's the way to start. Go back and remember, current through a coil can't change instantaneously, so the current starts at 0. The current in the resistor has to start at 0. And the inductor can't stop the current, it just slows it down. And since the inductor, remember, the inductor has no intrinsic resistance of its own, the ideal inductor. So once the current gets to its final value, it will rise to a final value. And like a capacitor, it does so in this manner. And so it rises to some final maximum value that we might call I max. And we can find I max by simply taking V max, the maximum voltage that you can get across the resistor, divided by the resistance of the resistor. So you see we get an I max of 6 volts divided by 3 ohms, 2 amps. So this value, I'm not going to try and write it in, this value of I max, where I drew the line, is 2 amps. And if you remember from capacitors, this behavior happens in a way such that during every equal interval of time called the time constant, the current rises about 63% of its final value. So during one time constant, the value rises to 63% of the 2 amps, then another 63% of what remains, then another 63% of what remains, and so on, as it asymptotically approaches this line and the maximum value of 2 amps. Okay, I hope you can see that what that means is that since the current rises, the voltage across the resistor has to follow the current, right? Right. The voltage across the resistor, let me go back to my thick pen, I like that better. The voltage across the resistor is going to simply be the current through the resistor times the resistance of the resistor. So the voltage, when the current's 0, the voltage is 0. When the current rises to 2 amps, the voltage will rise to 6 amps. So from 0, I didn't position that quite right. The voltage rises asymptotically to 6 volts. And okay, so let's review how we got there. We got there knowing that the current through a coil can't change instantaneously. It had to start at 0. So it starts at 0, it goes to its finest maximum value. The voltage across the resistor is determined by the current in the resistor, so that has to follow that. And so the voltage across the resistor is going to go to 6 volts, where it matches the battery voltage. And in the meantime, what's happening with the inductor? See if you can do that graph before I give it to you. Okay, for this part you want to remember Kirchhoff's law. The sum of the voltages around the loop rule, or the loop law. Sum of voltages around a loop have to be 0. So using that, we get that when the voltage across the resistor is 0, then the voltage across the inductor has to be 6 volts. Since the voltage across the inductor depends on, let me write that down, the voltage across the inductor, it's an induced voltage, it depends on, this is the equation I hadn't introduced, but in this case the inductance of the inductor and the, excuse me, that's wrong, rate of change of current through the inductor. That comes from a definition of inductance, which I hadn't mentioned yet. So the voltage across the inductor depends on the rate at which current is changing. And the change in current, this di dt, is the slope of this graph. So you see at the end, when the current's steady, the slope is 0, the change in current with respect to time is 0, the voltage across the inductor will end at 0. But during this period, the slope is at its maximum. In fact, the slope of this times the inductance will give us the 6 volts. So by Kirchhoff's law, the sum of the voltages around this loop have to always equal 0. Since this is 6 volts, the sum of the voltage on the resistor and the inductor have to add to 6 volts. So the graph looks like what? The graph starts at 6 volts and decays exponentially to 0 in such a way that at any instant in time, the sum of these two voltages, well, excuse me, this is the voltage up here, the sum of the voltage here and here, and the sum of the voltage anywhere has to add to 6. So at time t equals 0, voltage across the resistor 0, voltage across the inductor 6 volts. After one time constant, just trying to make all this work, this will have gone to about 63% of 6 volts, and this will have decayed from 6 volts down to a remaining about 36%. And so if you add this voltage and this voltage at any instant in time, they'll add to 6 volts. Okay, let's finish the circuit. We're going to, the switch, we left it closed here, remember? And we had reached all this final state of currents and voltages. Now we're going to take the switch from this middle position and put it into the lower position and restart the clock and plot I versus R, V, the current through the resistor, the voltage across the resistor, and the voltage across the inductor. And I've marked out on those graphs where the maximum value of each of those will be, and I've traced out 3 supposedly equal time intervals that we'll consider 1, 2, and 3 time constants. So make those graphs and then come back and check your answers against my answers. Okay, here we go. Remembering current through a coil can't not change instantly. So where were we left? We were left with the current high, 2 amps, I think, right? 6 volts divided by 3 ohms. So we were at 2 amps, and so what's going to happen is the current can't change instantaneously, so it's going to start at 2 amps, and it's going to follow an exponential decay towards 0. And remembering that the voltage across the resistor follows the current. So that graph has to be the same. They don't look the same, but imagine they are the same. And then remembering Kirchhoff's law, when the voltage is at 6 volts across the resistor, has to be at 0? No, it has to be at 6. Look at the circuit now. It's just this loop. So the sum of the voltages around this loop have to be 0. And so in this case, the voltage across the inductor is going to be equal and opposite at all times to the voltage across the resistor. So I don't want to plot that in the negative. So let me put some absolute value signs over this. It should be opposite in sign, and the curvature of that graph is going to be identical. All three will be identical, different units of course, but the same identical shape. So is that what you got? If so, good. So last step is to talk about or look at the equation sheet and see the equations that describe these 6 graphs. All right, remembering what we know about resistors and capacitors, and reviewing the format of those equations, and skipping the derivation by solving differential equations, which I might do in another video. We'll just go to the form of a charging exponential. Let's start with the current. So if we're doing the current across the resistor, it's going to be equal to I max in the case of the charging current, the rising current, it's going to be 1 minus e to the minus t over the time constant. And since the voltage follows the current, we could place the IR with a VR, and we could place the Imax with a Vmax, in this case 6 volts, and it's going to have the same time constant. In the case of the decaying exponential, like in the case of the VL or any of these, we would write that as VL, the voltage across the inductor at any point, is going to be the maximum voltage. 6 volts will be the max it can reach in this case. Simply e to the minus t over the time constant. And so for charging and discharging of any of those quantities, the equation is going to take one of those two forms. What determines the time constant? What determines how fast or how slow this thing will charge or discharge or reach its maximum value or go from its maximum to its minimum value? So what determines this time constant tau? Do you want to guess? What's going to make it longer? So pause for a minute and think. What in the circuit is going to lengthen or shorten the time? Okay, so if we have more inductance, that means more windings in the coil. We haven't talked about that yet, but if we have an inductor of higher inductance, that's going to cause a longer time constant. There'll be more opposition to the rising of the current, and it will slow the circuit down. If the resistance is higher, then there will be less the current, the maximum current. If we increase the resistance, rather than going from, say, 0 to 2 amps, we only have to go from 0 to 1 amp. So that means it will happen in a shorter period of time. So changing the inductance lengthens the time, changing the resistance by lowering the current shortens the time it takes to charge or discharge. So that's the time constant, depends on L over R. And so when we substitute that in here, we could write it as e to the minus t L over R, or we could make this into a simple fraction. I like leaving it as a compound fraction in this case because it shows the time constant. We could write it as T R over L. Could be written either way. Okay, I'm going to go back to the original because I like that better, because it shows the time constant as it should in the denominator. So I'm going to write it as T over L over R. Put in parentheses because that's the time constant.